Junior Cycle High Level 2013, Phase 3, Paper 1, Question 3. This is a sets question, and the first section is just making sure that you can understand the different types of sort of set notation explanation for a 3-set Venn diagram. So here we have A intersection B intersection C. So we're talking about the intersection of A, B and C. So what is the overlap of A, B and C? Well, that is this section here in the middle. It's where A, B and C are all occurring. For part 2, we've got, whenever you have something that's fairly complicated, where brackets are involved, you should always look at what is in the brackets first and visualize that before we worry about the rest of it. So here we have A intersection B. So where's A intersection B? That's the overlap of A and B, and what we're wanting to do is from that section we are lessing C, so we take away anything involved in C. So everything that is inside C, we're going to take that away. So what are we left with? We are left with a section that isn't in C, so the bit of the intersection that's not in C. So in part B now we have 6 statements and we're asked to check whether they're correct or not. And if they're not correct, or we find one that isn't correct and we show that it's not correct by some explanation, showing an example or doing a diagram. So what I'm going to do is I'm going to actually go through and talk about all 6 of them, because each of them have some learning and understanding that's useful in regarding sets for higher level. So the first statement we have is just straightforward A union B and B union A, and we're asked to decide whether this is true or not as a statement, whether they are equal to each other or not. So union is just when you're putting together sets and you include everything in the sets. So for A union B, we have everything that's in A unioned with everything that is in B. Looking at the second part of the right hand side, B union A, well, that's everything that's in B unioned with everything that is in A. And as you can see, those two areas are one and the same thing. And as a result, we can say that the two of them are equal to each other, and it's correct. I should point out to you that union is has the properties of commutability or commutative property. So A union B is the same as B union A. Just in the same way as 2 plus 3 is equal to 3 plus 2. You can put them in any order. That's what the commutative property is. Not only is union commutative, but also intersection is also commutative. Just as adding and also multiplication are commutative. Just to point out that there are some operations that aren't commutative, and we'll discuss this later on in part 5. So this part is correct, so it's not one that we would be able to leave as an answer to what has been asked of us here. It's not incorrect, so we can't. This will not be appropriate to be left as a solution to this question. So we'll move on to the next one. So part 2, the statement A union B unioned with C, whether it's equal to A union with B union C, and we're asked to check whether it's equal to it or not. So where is A union B? A union B, similar to what we've just done a moment ago, is that entire section, and we wish to sort of add to that set C. In the second, on the right hand side, we have B union C. So let's have a look at B union C. B union C is the section here, and we're checking to see whether and we're wanting to union A onto that. And you can see again these two areas are equal to each other. This statement is true, and we can therefore say part 2 is correct. This question is demonstrating the associative properties of union, which also is the same for intersection. The associative property is where you can group things in different ways. So, for example, 1 plus 2, and in brackets, then added on to 3, which is basically 3 plus 3, is the same as 1 plus 2 plus 3, so 1 plus 5. So the idea is you're grouping them differently, and they still give you the same answer. That's just the associative property. So in part 3, we're asked to evaluate whether A less B or less C is the same as A less B less C. It looks similar, but there's brackets around it. Now, to a certain extent, this is looking at the associative property, and you're being tested to see whether you understand which operations have the associative property. So this is, we're looking here at the less option or operation in sets. So looking at this question, we're asked A less B less C. So let's actually look at that. So we'll think about what A less B is. So A less B is everything that's in A, and from that we have to take away whatever is in B. So in this instance, we have this section here is in B, so we have to take that away, and this section here is in B, so we have to take that away. So that's just A less B. It's just these two sections here, this sort of moon shape. And then from that we are to less C, so take away C as well. So everything that's in C, well, this section here is in C. All the other sections are already not involved. And as a result, we have this section here. This is the section that's A less B less C. For the right hand side, well, let's just look at the thing in the brackets. So B less C, so what's in B but not in C? Well, it's this section here, it's B less C, and what we're being asked is we've got A less that section. So what we're doing is we're thinking about set A, and from that set we are going to remove what is in B less C, which in this case is this section here, and as a result we have as a set everything that's in A, take away anything that's in B but not C. Now you can see those two shaded areas are not the same because this area here includes these two sections here. So this statement is not correct as given, so we have to say that it's not equal. And in terms of a question that is relevant to what it was asking about incorrect statements, this here is an incorrect statement. It's not correct, and so we'll be filling it in this section here, and these two drawings, as you see here, are appropriate as a description of why it's not equal to each other, or how it is not equal to each other. Moving on to part 4, we're asked to look at the complement of A intersection B. So intersection is the overlap. So in this instance, this is A intersection B, and we want the complement of that. So the complement of this section here is everything else, everything outside of this area. So we want everything outside of this area here. And as a result, we have all the rest of the universal set apart from that section. And as I just described, that's basically the right-hand side. So we have the universal set, and we're going to take away the intersection. So if I imagine I've got the universal set, and from that area I'm going to less the intersection of A and B. So here's the intersection of A and B, and that section there is removed. And as you can see, those two statements are equal to each other, so it's equal. Along with the first one and the second one, they're all correct. And the only one we found to be incorrect is the third one. So far, anyway. Next, if we look at statement 5, so that's A less B and B less A. So if we just imagine what we're dealing with, we're talking about everything that is in A, but we are taking away from that anything that is in B. And we're left, as a result, this section, this moon shape section here. If we look at the right hand side, B less A, well, we're looking at everything that is in B, and from that area we are subtracting anything that is in A. And we're left this time with a moon shape, but it's a completely different moon shape. It's the B only section. So A only is not equal to B only. So this is a statement that we're asked to evaluate that is not correct. So we have two statements that we found to be incorrect, and then we have first, second and fourth ones that are correct. So this, if I wrote out the statement, this would be an appropriate set of workings to demonstrate that the statement 5, is incorrect. And this statement is an example to show that the less operation does not have the commutative property. So I can't swap around A and B and have the same result. Which is a bit like subtraction. If I said 5 take away 2, which is 3, that's not the same as 2 take away 5, which is minus 3. So the less operation does not have the commutative property. Last possible statement, we just have two expressions. Let's see whether they're equal to each other or not. We've got B less A union C. So let's just think about what is inside the brackets there. A union C is this section here, and I'm going to take that away from B. So B is this section here, and from that I'm taking away the section that is in white, that was in blue. Meanwhile, for the statements that are on the right hand side, we have B union C. So it's this section here, and from that I'm going to take away anything that's in A, and I'm going to take away also anything that is in C. And that, as an area that's remaining, is indeed the same. These two statements mean the same, and we can say they're equal. And as a statement, it's correct. So in terms of approaching B, your options are part 3 and part 5. They're the two statements that are incorrect. So you'd list one of those two, and you'd do the drawings as shown. But just in terms of learning, we've learned quite a lot just from looking through, and we've talked about the associative property and the commutative property. Now moving on, we have a standard sort of set problem question. and it's best done by using a Venn diagram. So a group of 38 students, so that's the universal set, were asked if they had ever been to France or Spain. The number who had been in Spain only was 3 more than the number who had been in both countries. Twice as many had been to France or Spain. 4 students had not been to either country. Find out how many people had been to both countries. So, as a statement, find out how many had been to both countries. This is the intersection, who had been to both France and Spain. So I'll tell you what, we might as well actually call that our value of x, our main unknown value. We're told that there are 4 people that had not visited either country, so we can put that outside of the union. The next useful piece of information is the one that states that the number of people who had been to Spain only, which is this section here, was 3 more than the number who had been to both countries. Well, both countries is x, so 3 more than that value x is going to be x plus 3. And our final piece of information is the statement that twice as many had been to France as Spain. So what they're saying is the total number of people who have been to France, including those people who have been to both, is twice as much as those people who had gone to Spain, which is 2x plus 3. So twice that is 4x plus 6. And we have x already in part of f. So we can look at f less anything in s. So we have the statement of 4x plus 6, and from that we subtract what is in the overlap, which is x. And we're left with 3x plus 6 for that section. Now we're asked to find out what is x, how many had been to both countries. And to do that, we need to appreciate that these 4 sections that we have here, when added together, make 38. So if I were to add them together, so x plus 3, and also 3x plus 6, and also 4, ties up to become 5x plus 13. Now all of that must be equal to the 38. So if we say that statement is equal to 38, take away 13 from both sides, and for 25, divide by 5, we get value of x is 5. Now, irrespective of what it's asking, you should always put any unknowns you found back into context, back into the equation, the Venn diagram. So x plus 3 is 6 plus 3, 5 plus 3, which is 8. X is equal to 5, and lastly 3 lots to 5 plus 6, which is equal to 21. So they're the sort of and we have our solution to the problem. We know how many had been to both countries. It's the overlap of S and F, and we get the answer of 5.